Hello and welcome to this tutorial on solving the induction machine equivalent circuit. So in a previous tutorial I talked about the equivalent circuit and how it was derived, and not wanting to recap that, the equivalent circuit is a resistance to represent the resistance of the windings in the stator, an inductance to represent the inductance of the stator, and those are called R1 and X1. A magnetizing reactance, what we call XM. And then to represent the rotor, we have another inductor to represent the inductance of the rotor, and a resistance to represent the resistance in the rotor. And it's called X2, and it's got a dash on it. The dash is to show the effects of the idealized transformer in the model and a few other things that are done to make the model accurate, but it's not actually the literal impedance. And also R2, and there's a slip function in there as well to represent the slip of the machine. So that's the equivalent circuit for the induction machine. It's quite straightforward. It's very simple. But if we've got a machine and we want to understand how it's going to operate in an environment, we want to model it, we need to use this equivalent circuit. But the equivalent circuit is no good to us unless we've got some values for it. And it's not like you can open the machine up and put an ohm meter across this and measure this. It doesn't work that way. The only access points we have to the machine, to this model, which is a two-pole model, is we can measure the voltage here and we can measure the current in. And as I said, this is a single phase model, so this is all we can do. That's the only thing we can measure. We can only measure the voltage and the current, and measuring these two things doesn't allow us to deduce what these are unless we alter the conditions of the measurement. So if we alter the conditions of the measurement, we effectively end up with what's almost like a series of unknown values for different conditions, which can be likened to simultaneous equations. And so there are three tests we can do. We can do a DC test, which is where we apply a DC voltage to this terminal and we measure the current going in. And that will give us a DC impedance, and we can use that to start doing some derivation here. The other condition we could do is we can lock the rotor, make this rotating speed of the machine equal 0 while we're putting a power into it. Effectively, the machine is stalled, so as I said, the rotating speed is 0 or slip will be 1. If you remember our simple diagram for the torque speed response for the DC machine, which goes something like that. Here's speed, here's torque. At this point here, slip equals 0, and at this point here, slip equals 1. And this is going to have a significant effect on this value here. The third test we can do is to run the machine up to speed with no load. And so we'll be operating it up about as close to up here as what we can get. Those three tests and the numbers we can get from that, we can then use based on these equations to solve for this, and that's what we'll do now. So as I said, the DC test, that's one of them, and that is used to find R1, so we'll make a note of that. The second test is called the locked rotor, and I'll just write lock, and that is used to find R2, X1 and X2. And as I said, that is with the locked rotor, so RPM is 0, slip equals 1. And the third test is the no load test, and that is used to find XM. So what we'll do is we'll go through, we'll pretend we've got some numbers. I've got a worked example here that I've done before that I show my students. It's already got the numbers solved for it, so I don't have to go through and recalculate it. We'll just go through that. So we're going to be measuring the voltage, we're going to be measuring the current, and we're going to be measuring the power. So for the DC test, we will say we've measured it and we've put 10.5 volts on the input and it is drawing 18.2 amps. And power is a product of those and not used for what we're going to be doing, so I won't bother noting it. For the locked rotor test, we'll say that it drew had 85 volts in it and it drew 19.2 amps. And for the no load test here, we'll say that we had 220 volts and it was drawing 6.2 amps at 395 watts. I forgot to mention up here the power, 695 watts. So we've done our 3 tests, we've got our data, we can now use this data to find out the values in our equivalent circuit. And the first thing we're going to do is we're going to use the first one, the DC test. Now, in order to understand what we're going to do with this, we need to remember that the impedance of an inductor is 2 pi FL. We've put a DC voltage in here, so the impedance to DC is going to be R1, but there's no impedance here, and the reason for that is because it's DC. If frequency equals 0, then inductance doesn't change, pi doesn't change, 2 doesn't change, but 0 times anything is 0. So this term here goes to 0. So from the DC purposes, for a DC test, X1 has got an impedance of 0. Similarly, X2 and Xm has an impedance of 0. So we come in here, the impedance our DC source sees is R1, nothing, nothing, and back again. If we go this path, we've got nothing, R2 over S, but this value of resistance is effectively short-circuited by this 0 impedance. So this is, we forget about this, it means nothing to us. So the only impedance is R1. So we need to understand whether this machine is connected in series, in delta or star, because then we can solve for R1. So if it's connected in star, we are effectively measuring there, in which case the impedance that we're going to be getting, bearing in mind that this is now becomes R1 for the 3 phases, R1 is going to be that voltage divided by that current divided by 2, because there's 2 of them there. If it's connected in delta, we would be measuring that, in which case R1 is 3 times the voltage over twice the current. So what we'll do is we'll assume one of them, we'll pick one of them. We'll pick this one here. So R1 is our DC voltage, which is 10.5 over 2 times 18.2, and that gives us a resistance of 0.288 ohms. That's all fine. That's good. What we now need to do is we need to start, now we know R1, we need to start finding these other values. So what we can do is we can take into account the impedances here by a simple power calculation. We know that power is I squared R, and this is for our three phases, so three times the total power that we're measuring, 3 times the input, squared over R1 plus R2. What we can then do is rearrange this. We know what the input current is, we know what the power is, because we've got these two values here. What we can then do is rearrange this, and we know what R1 is, so we can solve for R2. So therefore, R2 is power over 3 times our current squared, which is 695 over 3 times 19.2 squared, which gives us a solution of 0.34 ohms. Now that we've found R1 and R2, we now need to move on to the next ones here. And the next one to try and find is X1 and X2. So, how do we find X1 and X2? We know that the impedance here is voltage and current, Ohm's law. We also, at this point here, are going to make one of the first of assumptions that we make when we're building models, and that is that the value here of Xm is high. So we're not going to worry about it. So what this tells us is that the impedance is the line voltage over the phase current, which is the same as saying this impedance in series with this one, in series with this one, in series with this one. Which is R1 plus R2 squared plus X1 plus X2 squared. Now we don't know what this is, but we know what this is, 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 we don't know what these are. So we're going to treat this as a whole, go through and solve for X1 plus X2, and then make our second assumption, which is that these two values are roughly the same. So if we solve for this and then halve it, we will get our values for X1 and X2. So to do that, we rearrange this equation here, and that rearranges down to X1 plus X2 equals square root of our phase voltage over our current squared minus R1 plus R2 squared. So we can go through and punch some numbers into that. So this is the phase voltage that we're looking at here, because it's a single phase model. We've got a line voltage, so we need to adjust for that. Important note, this is where a lot of students, they go wrong, put the wrong values in. So we end up with here with being 85 volts that we measured, which we need to divide by root 3 to convert it to our phase voltage. and that is over our current, which is 19.2. All of that gets squared minus R1, which we have solved to being 0.288, plus R2, which we found to be 0.34. All of that squared, and then the square root of all of that. And if you go through and punch those numbers, you end up with 2.47 for being x1 plus x2. And as I said, the second assumption that we make is that x1 and x2 are roughly the same value, so therefore x1 equals x2, which equals 1.23 ohms. So we now have the values for R1, R2, x1 and x2. We now need to find out the value for xm. To find the value for xm, we go to a no-load, that's a no-load test. In our no-load condition, our speed is up here. And so our speed is close enough to, well, it is at the maximum speed, and so therefore the value of slip is not quite zero, but close enough to zero for our third approximation that we will assume it is zero. By assuming that slip is zero at no load speed, anything divided by zero is infinity. So our circuit now becomes this. So with our no-load values of here and here, we've got R1, which we know, X1, which we know, in series with XM. So once again, we can use that very same process that we did up here, where we know that the impedance is our voltage over our current. But in this case, it's going to not equal that, it's going to equal these ones. So it will come down to being the square root of R1 squared plus X1 in series with XM all squared. And what we can therefore do is rearrange this for XM. And that will be our voltage over our current. Again, that's our phase voltage. All of that is squared minus R1 minus X1. And if we pump the numbers in there, again we end up with 85 over root 3 divided by, sorry, not 85, 220, my mistake. We're using common mistake. We've got to use the values for the no-load test. So that's 220 over root 3, and that will be divided by 6.2 amps. All of that squared, minus the value for R1, which again back here, 0.288, minus the value for X1, 1.23, and there's a square around all of that. And if we go through and solve the numbers for that, we end up with an impedance of 19.25. So that is how we solve the induction machine equivalent circuit. What we did was we've got our equivalent circuit, we've subjected it to a DC test and got these values, a locked rotor test, got these values, a no-load test, and got these values. What we then do, the order that we go through is in that we go through and solve for R1, we then solve for R2, we then solve for X1 and X2, and then for XM, using the different values that we obtained for the different tests under the different conditions. That's how you do it. It's quite mechanical. I have an Excel spreadsheet set up which goes through and does all these calculations for me. I suggest you do the same. Thank you very much for watching. Look forward to seeing you again.